right, thanks a lot. Thanks a lot for the invitation. It's always, it's a great feeling to be back at Berkeley, seeing all the familiar faces and the familiar room. So I'd like to tell you about some work that I've been doing for the past year or so with my collaborators Ji Dong and Don Marolf at UCSP, which should hopefully appear sometime soon. So let me get started with the players of the game. So the first thing that it said is the JLMS formula. So let me remind everyone what the JLMS formula is all about. So the relative entropy is defined as this quantity, which basically measures, it's a measure of distinguishability between two particular states, let's say rho and sigma. And the JLMS formula, as told to us by these authors, says that in holography, the relative entropy computed on the boundary for some subregions, capital R and capital R bar, is to leading order the same as the relative entropy computed in the respective entanglement wedges. So for capital R, the entanglement wedge is this region little r, which is bounded by the extremal surface gamma r, which is the Ryutakianagi surface. And the relative entropy computed in the bulk on this region matches the relative entropy on this boundary region. Now that's one version of the JLMS formula, but the one that I'll be more interested in this talk is what you should think of as the operator version of the JLMS formula. So just by considering perturbations to the state and using the FLM formula, these authors had derived this particular form of the formula, which says that, so firstly, define K, to, the modular Hamiltonian, to be minus log of the density matrix. Hopefully this is something familiar to everyone. And then what their formula says is that when you consider perturbations to the state, you pick some code subspace in the bulk and consider arbitrary states within that code subspace. Then the modular Hamiltonian on the boundary, appropriately projected onto the code subspace, is equal to a term which you can interpret as the area operator, which basically evaluates the area of a given geometry over 4G, plus the bulk modular Hamiltonian in the entanglement wedge. Very often people ignore these projectors, but it'll actually play an important role here, so I'd just like to make note of that. And the reason is because the modular Hamiltonian on the boundary it generally lives on a larger space. So the boundary Hilbert space is much larger than the code subspace. And so all by just doing these perturbations within the code subspace, all you can say is that when projected onto the code subspace, there's such an operator relation. All right? Yes.
That was log you're taking to get the modular Hamiltonian in the bulk is sigma?
Good. So here it's kind of implicit. It's true for any, so this formula is true for any state within this code subspace. So let's say it implicitly has a rho in it or sigma, either of them. Yeah. So in particular, you could have taken expectation. So if this was an equation I wrote for rho, you could take the expectation value in the state rho, and that would give you the FLM formula. But this is a more general statement, and you can look at the expectation value in arbitrary states in the code subspace. All right. So just as brief motivation, why should we care about JLMS? Well, historically, it played an important role in our understanding of bulk reconstruction. So as shown by many authors, a nice way of interpreting holography is as a quantum error correcting code, where the statement is that when you have an error correcting code with this property of subregion duality, which says that any operator in the entanglement wedge little r can be reconstructed on the boundary capital R. This property is in one-to-one correspondence. It's equivalent to having something like an RT formula with FLM corrections, and also is equivalent to having the JLMS formula. So forget about holography, just any exact quantum error correcting code with this property of subregion duality has something that's like the JLMS formula. it's a pretty universal feature of error correcting codes. But in particular, we'd be interested in understanding this in holography. Now, this was the story for exact error correcting codes, but you can also think about what happens when you slightly disturb this. And if you only have an approximate equality between the relative entropies in the bulk and the boundary, then it was also shown by some other authors that there's a reconstruction map, which is the twirled Petz map, which you can use to then reconstruct operators in the entanglement wedge just using the region that you had access to. So even having an approximate form of JLMS is sufficient to guarantee that you can reconstruct, so you have a good reconstruction fidelity for operators within the entanglement wedge. Right? Okay, good. So with the JLMS formula out of the way, let me tell you about the other player, which is the Kink transform. So this is hopefully familiar to some of the authors who are here. And so in this paper, we discussed this Kink transform, which is, oh, it's not very clear. So in the gravitational theory, you should think of the Kink transform as just some transformation of the initial data on a Cauchy surface, which contains the extremal surface of interest. So if you have two regions, R and R bar, their extremal surface is here. Consider any sigma which includes gamma R and transform the initial data as follows. We keep the induced metric the same, but just change the extrinsic curvature data by a delta function. So we shift the extrinsic curvature by a delta function, which basically creates this kink. So you go from this straight slice to this kinked slice. This is firstly a valid transformation on the initial data. Whenever you have some initial data, you need to check that the constraint equations are satisfied. And you can check that in Einstein gravity, this actually gives you good constraint data for initial value, for the initial value problem, which you can then evolve and find a new solution. And in general, just because you've kept all of the data within each of these halves of the slice the same, just by causality, it evolves into two wedges which are identical to what you had before. So you have one copy of this left entanglement wedge and one of this right entanglement wedge. But now, because you've glued them together in a slightly boosted fashion, the regions which are to the future and the past are not in general going to be the same anymore. So it will be some non-trivial solution that's changed in the future and the past. And in general, it's hard to solve. I mean, there's no easy way to figure out what the geometries look like in the future and the past, but it at least gives you an in-principle initial value problem that is well posed, and you can solve for this new geometry. So this is an easy transformation which generates new solutions. Okay. So we were interested in understanding the holographic dual to this transformation.
So
yeah.
For this Kink transformation,
yes.
To get good initial data,
yes.
It has to be done in extremal.
Oh, sorry. Yeah, that's a very important point. Thanks for that. So the fact that this satisfies the constraint equations crucially required that this surface is an extremal surface. If you tried the same thing about a non-extremal surface, this would not give you good constraint equations. So it definitely picks out extremality. Yeah. Any other questions? All right. Good. So we were interested in the holographic dual to this transformation, and we proposed that there's something called the con-cocycle flow, or CC flow, which is defined as follows. So you start with some state psi, and in general, the con-cocycle flow is defined by modular flow, where you forward modular flow by one state and then reverse modular flow by a different state. So here, the two states that I'm considering are rho and omega. So you first flow by an amount lambda with the modular Hamiltonian for rho, and then you flow by minus lambda with k omega. Now, in general, you could consider any two states that you like, but for the purposes of relating the Kink transform to some nicely known holographic dual, what we needed to do was consider rho to be the density matrix that's obtained from the state psi itself. So if you just take psi and trace out one of the subregions, you get some density matrix rho, and you flow by that particular modular Hamiltonian. And then you reverse flow by what's the vacuum modular Hamiltonian. And this, the cases that we considered in that paper relied on situations where the vacuum modular Hamiltonian was local. So it had a nice local action. It was just a symmetry transformation. For example, in half space in Minkowski, we know that the vacuum modular Hamiltonian is just a boost generator. And similarly in the thermofield double, where it's just a time translation. So in those cases, the action of k omega is simply a large diffeomorphism. So on the boundary, it's some symmetry transformation, which is just local. It just moves you from one slice to another. And the bulk dual of this is that you're just looking at the same space-time, but now you've moved your time slice in some way. So for example, in the thermofield double, you'd have the same space-time, but all that this part would do would be a relative time translation. You just have the same state, but time translated. So really the important part of this duality was the first part. So if we forget about the transformation that the vacuum modular Hamiltonian, which was a symmetry transformation here, did, then the statement essentially was up to that diffeomorphism, the state that is generated by considering one-sided modular flow on the original state that you had is given by this Kink transform. That was our proposal. And there was a lot of evidence we had for this. There was firstly, so essentially every property that was known about the Concho cycle flow, which is not too many properties, every property that we know from the boundary side was reproduced by this. And further, there were like non-trivial things like the Concho cycle flow has stress tensor shocks on the horizon, and you could exactly reproduce it by the features of the Kink transform. For example, the Kink transform had some wild shocks in the bulk, which exactly matched on to these stress tensor shocks. So it was a pretty non-trivial matching. So there was a lot of evidence that this duality is accurate. Yeah?
Do you also assume K rho is geometric?
I'm not assuming anything. I want to prove it, but
in general, K rho is not geometric, but K omega is geometric.
That's correct.
But you say that when you combine them together, you get something geometric.
No. I want to actually say that K rho itself, in some approximation, which most of the talk is going to be about explaining in what approximation. But in some approximation, the action of K rho is indeed geometric in the bulk, not on the boundary. On the boundary, it's some non-local mess.
Your statement that this CC flow
Yeah.
is a Kink transformation
Yeah.
is approximate or exact?
Well, it's approximate, but depends on like in what parameter you're interested in. Like, I mean, for example, this like you could consider like G Newton corrections or whatever. I don't know.
No, but it's not approximate in the sense of deviations from a geometric modular Hamiltonian. It's totally okay for these to not be geometric, right? K omega and K rho.
Well, K omega we need it to be geometric, but K rho not necessarily so. Because we're looking at these special cases where it is geometric, K omega. But K rho, what I mean is on the boundary, it's not a geometric object. It's not it's not a boost transformation or anything like that. But in the bulk, the geometry that you get from doing this Kink transform is the dual to the thing that you get from this flow. So it does, in the bulk picture is nicer than the boundary picture in that sense. Like the
boundary picture is pretty nice too, right?
Mm-hmm.
Because what it really does is it just takes, so if you take a quantum state and you do a half-cycle boost to it, classically that's something you can do. drawn for every node all the way to the UV.
Yeah.
And what this flow basically does is it fixes that. So its effect is to basically change all the initial data as if you boosted one side, so all expectation values change that way, but without breaking the vacuum at the seam. So it's a pretty simple state in terms of, yeah, expectation values on the left and the right. They're just boosted.
I understand what you said, but what confused me is that I thought in general K rho is not geometric.
It's acting on psi. It's acting on the same
On the same state.
that it was defined with.
So
that makes it nicer.
Oh, I see.
Yeah, I mean, so this action, I mean, if you just looked at any correlation functions just on one side,
Yeah.
it doesn't even change because this is just a symmetry of the state.
Okay.
So in that sense, it's nicer. But still, again, even in the boundary side, like once you do this, like each wedge doesn't change, but because they're glued differently, like the evolutions will change. So that part is still non-trivial. But you can, yeah, I mean, it's still preserving the data on each of the subregions, like just within those. Yes.
So consider the TFD, consider the CC flow on the TFD.
Yeah.
Does that give you a state at the t equals 0 time slice?
So
Delta function.
yeah, so this state would give you a state on the t equals 0 time slice. And then it's like, I mean, when you had this particular slice, if you just did the modular flow, then you would think of the boundaries of this as the original R and R bar. So it's still the t equals 0 slice on the boundary. But then if you also do this vacuum modular flow, then it'll sort of send R up. Like then you can think of this as the t equals minus lambda slice or something. Like,
So the first modular flow gives you some kind of shock,
yeah.
and the second one fixes it by boosting.
Yeah, that's right, that's right. So this state in general is pretty singular when you have like endpoints of the subregion. And this sort of fixes up the singularity in the vacuum, singularity in that state near the entangling surface. But yeah, you could imagine like regularizing it in different ways. I mean, you could do something else that fixes up the vacuum. These were just nice cases where like the action of this vacuum modular Hamiltonian was simple, and we could just understand that.
Does,
Sorry, go ahead.
does the vacuum modular Hamiltonian acting by itself give you a good state?
Not by itself.
I see.
It's similar to modular flow in that sense.
Yeah.
Yeah.
These are full modular Hamiltonian.
No, good. So these are half modular Hamiltonian. These are one-sided modular Hamiltonians.
What does that mean?
What does that? You mean like rigorously, or?
Is it half-sided modular Hamiltonian? I don't know.
Okay. So the modular Hamiltonian is just minus log of the density matrix. So once you define the density matrix, it's just that. The full modular Hamiltonian is like the difference of the right modular Hamiltonian minus the left modular Hamiltonian.
I thought that's the only thing that's well defined.
Well, okay. So it depends. Okay. So
Because it's down to k omega, but you're doing k omega.
yeah. So okay. So this state is rigorously defined in QFT. Like you can take the continuum limit and it's well defined. The state this state without a regulator is not well defined.
I think that the right way to, I think what you're saying is morally correct, but I think the more rigorous way to do
Yeah.
this is
Yeah.
that both of these be full
That's
modular
right.
Hamiltonians,
Then
and then show that the action of the combined operator is trivial, or that this is really the
Yes.
output of only one side.
that's right.
That it's trivial on the other side.
That's right. That's right.
Because that way you don't have to introduce any cutoffs or anything to regulate.
Yeah, that's fair. And in this talk, I will be interested in understanding one-sided modular flow. For simplicity, we can think about this as just talking about situations where the region doesn't have an endpoint. Then you don't have to worry about any of this, and you can really write this formula the way I've written it, because then you don't need a regulator. In situations where you do have endpoints, then you need some regularization, and then we can discuss that subtlety separately. So for simplicity, let's just think about these as like, I don't know, asymptotic boundaries or something. Then each of these is defined, and I can define the Concho cycle directly this way.
Yeah. I think maybe just to add to the situation that I tried to give earlier.
Yeah.
where fixed slice, it doesn't kink it, but it produces a state that is the forward evolution of just a boost on one side and then put it on the kink slice and then evolve it back forward.
Yep. All right. So, I mean, in the situations of interest that we talked about, because this was a symmetry transformation, I'm just going to forget about this vacuum part for now and just look at this portion, which is just the one-sided modular flow. And as I said before, because of this symmetry transformation, this is related again to the Kink transform, but up to this identification by a large diffeomorphism. All right? And that's what I'll call the boundary condition preserving Kink transform. So it's some version of the Kink transform up to this diffeomorphism.
Yeah,
Yeah.
Sorry,
Yeah.
this is something I thought in general, it's if you just look at e to the minus I k rho lambda times psi.
Yeah.
And the k rho is, I thought in general that's bulk modular Hamiltonian, right?
Sorry, this is the boundary modular Hamiltonian.
It's a boundary modular Hamiltonian, which is the same with the on the bulk. It's a bulk.
Well, it's not the full bulk Hamiltonian. So up to the area term.
I just thought in general in the bulk it's not geometric.
Okay, good. Okay, good. So let me just, so going forward to what I'll eventually say is that I'll ignore effects of the bulk modular Hamiltonian, and the Kink transform will basically come from the action of the area operator.
That's why I was asking, is it approximate?
Yeah, I mean it's approximate in this sense.
In the sense that you only take the area operator, that's why the only change happens at the bifurcating surface.
Yeah.
Okay.
Yeah. I mean, there's probably some more sophisticated version of the Kink transform where you also update like the bulk quantum state and so on, which will work more accurately. But yeah, it's the area part which will give us the Kink transform. Yeah, that's right. Okay. Good. So good. So why care about modular flow? Well, it's been useful in a bunch of things in holography. Reconstruction maps, for example, rely on this fact that there's this equivalence between bulk and boundary modular flow. The proof of the quantum null energy condition and other insights that we've had into quantum field theory has come from trying to understand modular flow and things like Tomita-Takisaki theory. Moreover, people like Lamproche have talked about the proper time flow in the bulk, which is also given by some modular flow. And in general, it's a pretty complicated thing, as you already pointed out. In general, there's no nice situations where we can actually have a handle on this. And so it's pretty useful to have control over it in some nice limit. And this particular limit that I'm interested in, where you have holographic states and we're just looking at the leading behavior of this from the area operator, is one nice situation where we have some handle over it. And in general, we just don't. So it's nice to understand what happens in this situation. And there's been a lot of work about this. People implicitly have sort of relied on the Kink transform in computing things like modular float correlation functions, because holographically computing modular float correlation functions in general, again, is pretty hard because we don't understand modular flow, but this simple picture holographically gives you a handle on computing it sometimes. So that's why, so that's part of why you should be interested in modular flow. Okay, so finally, with the introduction, let me just tell you the goal of this talk. The goal of this talk will be to derive the fact that the one-sided modular flow is given by this boundary condition preserving Kink transform from first principles. So we want to do this in holographic theories, general holographic theories, so not necessarily just Einstein gravity, but maybe higher derivative theories and so on. But in a way, the thing that we did in the paper with Raphael is, you can think of that as a proof of the fact that the Concho-cycle flow is given by the Kink transform, because we basically matched everything we knew about the Concho-cycle flow. I think what distinguishes this talk from that is trying to derive it from first principles of things we already know in holography and trying to use those and concretely say that there's some precise sense in which the modular flow is given by the Kink transform. So that's sort of the goal of what I want to talk about.
This is in specific states?
So it's not going to be, so it's for general subregions and general holographic states. But when I say modular flow, I mean like modular flow in this sense, on the state of interest. Like you take some state, take that density matrix, and modular flow the same state.
Yeah, so on this slide you mentioned cases with, no.
Oh, sorry, here. Yeah.
Where K omega is symmetry transformation, so you're not doing that.
Yeah, so that's about the subregion, and I'm not restricting to whatever, some kind of subregion. I think the important point is that we had to restrict to particular subregions because we cared about this niceness of the QFT state, and we had a concrete way to like make this state a nice state in these situations just by doing the symmetry transformation. But I think the story is a little more general than that, in that you can consider this object for arbitrary subregions, and it still does something like the Kink transform. You still have this issue with the singularity, but you could imagine fixing it in some other way. You don't need a nice local modular flow to fix it up. There's still some sense in which this object itself is approximated by the Kink transform. How it picks out.
You're doing only one.
How it picks out a psi? Oh, sorry. So I'll hand you a psi. You take the rho that you get from that psi, and you modular flow that psi with this rho. You don't get to act this rho on like other psi.
So again, you're thinking of this as a half-sided modular?
Yes.
Are you going to recover the? So here we didn't have to do that, right?
Yeah.
So we didn't get any violet shocks.
Yes.
We got these sort of integral ones. And then are you departing from that?
So I think of this as like, I think of that as a special case of this. So once you convince yourself that in some regulated version, this state is the Kink transform, we know what the action of this object is because it's just a symmetry transformation. And once you do that, you can take the regulator away and you recover whatever we had earlier. But with a regulator, it's a more general thing.
So the regulator is essential.
It's essential if you have boundary endpoints. You can also talk about this if you don't have boundary endpoints, like the thermofield double. Maybe you have like a time-dependent geometry on the boundary or something. And
should not depend on that, right? Let's think about the CFT.
Yeah.
Assuming that this state has a finite energy excitation.
Which state? The modular flow?
Psi.
Oh, psi itself, yeah.
And then I think this singularity comes from arbitrary high energy thing.
Yes.
So if you just flow backwards, it shouldn't depend on how it's regulated. You can regulate it to hyper-distance with the energy excitation of psi.
Sorry, you're saying when you flow back with the vacuum modular Hamiltonian, then you can take away the regulator? Yeah, I think that's true.
Always, yeah.
I think that's true. But I think Raphael is asking, like, if you don't do that, then, like, I mean, then you need a regulator to make sense of the state. Right?
Yeah, but that regulator is sufficient. You take the limit. It's a small, for example, the regulator to be very, very small cutoff. Then it should uniquely go back to the unique result. Should not depend on how you regulate it.
Yeah, but the state that I will be talking about mostly is just this part of it, which is singular. So you need a regulator to even. So you can do that after you've got control of this state. You can do this and then do what you said, like just take the regulator away, and then it's fine because it's a non-singular state. But even at this point, I think there's a nice geometric picture just for this itself, as long as you use a regulator.
Okay, then you.
I think that's what he's saying. Any other question? Okay, good. So let me just outline the steps that go into trying to prove this. As expected, we start from the JLMS formula because we need the modular Hamiltonian. But in trying to realize that, we And since we're going away from just exact quantum error correcting codes, we're thinking about approximate quantum error correcting codes here. We actually realized that there were some subtleties with understanding the JLMS formula in this operator version. And we'll actually have to restrict to a particular class of states that we call log stable states. So I'll tell you a little bit more about that. Once we have that, then we want, since we want to take the modular Hamiltonian and exponentiate it to get the modular flow, it's actually non-trivial to even take the JLMS formula and find an exponentiated version. It turns out that you need a particular form for the code subspace. We will get this by building out this code subspace from fixed area states. I'll say a little bit more about it when I talk about that part. Once you have this exponentiated version, then it's similar to what Ying was saying, which was you have modular flow, which is given by an area term plus like a bulk term. And we want to argue that the modular flow is well approximated by the area flow. And this is not in general true, so I'll tell you about when that approximation works. And finally, what we'll do is now take the area flow and show that the area flow itself generates a Kink transform. And the more general version of this in higher derivative theories would be that the Dong entropy is the thing that generates the Kink transform. And for this, we'll use classical phase space techniques like the Piles bracket. So that's sort of the outline. So going from the JLMS formula to the Kink transform. Is that clear? Okay, so good. So let me start with the first question, which is when does the JLMS formula even hold? This was a question that we analyzed in this paper with Jonah Kudler-Flam earlier this year. And so just to remind you, the way that JLMS is derived in the first place is by starting with the Euclidean path integral, deriving something like the FLM formula, which requires replica symmetry. There are situations when when replica symmetry fails and subleading replica symmetry breaking saddles can become important. And a lot of this has been analyzed in the last few years. For example, near entanglement phase transitions, you can have these corrections of order 1 over square root g, which was analyzed in these papers. And more so, you can also have leading order corrections, as was discussed by Akers and Pennington, when you have these incompressible states where the one-shot entropies don't agree. If you don't know enough about this, it's fine. The only important point here was that there are situations when the quantum extremal surface formula itself has large corrections. When the quantum extremal surface formula itself has large corrections, naturally you should expect that the JLMS formula also has large corrections, and I won't be able to do anything in those situations. But those are situations where the entanglement wedge itself is not very well defined, and so it's perhaps sensible that we can't do much. However, what we noticed was that even the quantum extremal surface formula corrections imply JLMS corrections. It doesn't go the other way. So there's actually more ways in which the JLMS formula can fail than just the ones where the quantum extremal surface formula fails. And the ways it fails is easy to understand from just re-deriving the JLMS formula. What we do when we derive the JLMS formula is linearize the FLM formula. So we consider a state within the code subspace which is deformed from some original state, and we consider the variation in the entropy under that deformation. Usually what we do is just keep this linearized term and use that to derive the the JLMS formula. However, there are higher order terms, for example, this second order term, which actually isn't always negligible. So an example of this is if you consider states which aren't necessarily full rank, or if they have sufficiently small eigenvalues, then because of this rho inverse that's here, the correction from this could be large enough to pollute the derivation of the JLMS formula. These are situations where you can actually find all arbitrarily large violations of the JLMS formula. So there were some toy models like the PSSY model that where we could do the path integral more accurately and see that in the bulk and the boundary you can have relative entropies that are arbitrarily different, like they can be very different from each other. even though these are situations where the entanglement wedge is well defined. So you'd think that something like the JLMS formula should work. So this is just a gap between exact error correcting codes and approximate error correcting codes. We should always think about holography as having these approximations because there's non-perturbative effects that we don't completely understand. And so in holography, there are many situations where even though the entanglement wedge is well defined, you can have these large corrections to the JLMS formula. So the key point is that JLMS is a strong condition. It implies reconstruction because JLMS is a pretty sensitive measure of distance between states. So if two states are close in the relative entropy, then they're also close in other measures like the trace distance. But it's not the other way around. So you can have states which are pretty close in trace distance. So for all practical purposes, they have similar correlation functions and so on. So they have similar geometries and similar answers for most of what you can compute. But JLMS fails by a large amount. So the key point is just that you need to restrict to some class of nice states, which is what we call log stable states, where you don't have too small eigenvalues so that you can actually use the JLMS formula. Yeah.
What does that mean that this formula fails like significantly? Does that mean you don't have a nice, you like honestly don't have a nice bulk picture for it?
No, you do have a nice bulk picture, so that's the thing. So
You
just,
can't always use it or something.
sorry?
You can't always use it.
The derivation of the JLMS formula is what fails. So for example, the simple thing that we considered was like in the PSSY model, you can have like brain flavors, which are like your code subspace, and you can have states which are say orthogonal flavors on the brain. Those have infinite relative entropy in the bulk, but on the boundary, they have a large but finite relative entropy. So the relative entropies are like off by an arbitrarily large amount. This doesn't necessarily mean that the states, like if you measure correlation functions, these two states will, I mean, you can, they're not that different.
I thought in the West Coast model that those two states were ever completely orthogonal.
That's fine. So this is, I mean, even if you have like states which are or slightly, not completely orthogonal, but slightly orthogonal, they still have infinite relative entropy. Because it's just pure states. I mean, as long as their supports don't match, then you can have infinite relative entropy. But the key point is you need to restrict to some nice class of states for JLMS. It's not an issue with entanglement wedge reconstruction. You can still check that the PETS map, for example, will work just as well.
So is
Yeah.
is it boundary?
Yeah. So when we do this linearization, we do this both on the boundary and the bulk. So the same story holds for both bulk and boundary.
But just for 1+1 CFT, I expect that I will have very small eigenvalues in the reduced density matrix. Say for a single interval.
Very small. You mean for the vacuum?
Yeah.
Yeah, it depends on, so when I say small here, I mean parametrically in G. But there, like in a 1+1 CFT, I don't know if yeah, I think I should say that, I mean, so in the bulk, let's say in the bulk, you'd have some field theory which will have some similar features, but then in order to even make sense of the state on one side, we're using some regulator, right? Like to talk about the density matrix itself. I think the regulator should control those eigenvalues then, because the rank will then be constrained and so on. Yeah.
Thanks.
Yeah. So it's some truncation of the state.
So what do you mean by the reconstruction without JLMS? How do you justify let's recover?
You can't, that's the thing. So you need some separate argument. So JLMS was really useful because it gives you a justification for why reconstruction should work. But the point is that it's a really strong condition. There are other situations where reconstruction works, but JLMS is not an indicator for it. That's, yeah. All right, good. So then we arrive at the question of what code subspace to use. So in order to derive something like the Kink transform, we at least need a code subspace that's different from what's usually considered. Usually in ADS-CFT, people just considered one background and like small perturbations on top of that particular background. But in order to derive something like the Kink transform, you at least need a sufficiently large code subspace which has multiple background geometries so that you can flow from one to the other. And moreover, one of the issues that I talked about briefly before is that even if you have the JLMS formula, it's non-trivial to find an exponentiated version of the JLMS formula. And the reason is because of these projectors. So the JLMS formula is this, where it has the projectors around the K. But when you try to exponentiate it, essentially, in order to get a formula of this form, you need to move the projectors past the modular Hamiltonian. This is only true if the modular Hamiltonian approximately commutes with the projector onto the code subspace. And essentially, you can show that this is only true when you have a flat spectrum. So you need approximately a flat spectrum in the state in order to be able to exponentiate this formula. Now, so the natural thing to consider is gravitational states which have these flat spectra. And we considered these a few years back. They're what are called fixed area states, where you just take the original state that you have and just think of it as putting like a microcanonical window on the area where you allow fluctuations to be parametrically small so that the area doesn't change too much. If you do that, the Renyi entropies that you get are all flat as a function of n. And so with that condition, it's sufficient to see that the code subspace is then, it commutes with the modular Hamiltonian at leading order. So this is sort of a useful technical trick in order to go through with the proof. Yeah.
For fixed area states, do you have any state of quantum fields?
Yeah, so roughly, I'll just get to that on the next slide, but you basically want to fix one background with a fixed area state and then allow some excitations on top of that. So build up some excitations on top of that. Yeah. Oh.
Does it affect, you're not saying that the claim that we made in our paper is restricted actually to fixed area states?
No. So fixed area states, so what I'm going to do is, so the fixed area state will, maybe this will get clear on the next slide, so I'll just get back to you. Okay, good. So what we're doing is first building what we call a small code subspace, and that's what we use the fixed area state for. So this H alpha is defined as some fixed area state plus excitations on top of that background. And importantly, we need to fix, when in these discussions of fixed area states, there's an important parameter which is the exact width of how much fluctuations you're allowing in the area. If you allow it to be parametrically larger than order G, then you do have a semi-classical spacetime, like you can solve for, you have a nice Lorentzian spacetime everywhere, which some examples were shown in this paper. But in general, for the purposes of this talk, we'll need the area to be parametrically smaller than order G. In these situations, just from the uncertainty relation, you can see that there's no nice future and past evolution that you can have. You still have the two wedges that you're interested in, but just because there's a large fluctuation in the conjugate to the area, which is the boost angle, you don't have any nice description for the future and past. So in some sense, they're singular states that way. So for this small code subspace, we'll also pick some size of the quantum field theory subspace to be order 1. So it's some order 1 number of excitations on top of this background. And then we can prove this theorem, which is approximate JLMS in this fixed area code subspace, which essentially says that if you have something like approximate FLM, so you have some FLM formula with some error, and you use log stable states, which essentially say that you don't have two small eigenvalues either in the bulk or on the boundary, then you have this operator version of JLMS up to some order square root G errors. So within this, it's pretty straightforward to prove that you have this approximate version of JLMS. Now, this is a pretty restrictive setting because this is just one background with the particular fixed area state. But what we'll then do is build up a large code subspace. So what we'd like to do is patch up these different fixed area states. Just think of a direct sum over each of these. This is something that has a long history, goes back to Harlow's paper on the RT formula and so on. But what we'll do is take each of these, each of which we know satisfies a JLMS formula for log stable states. And we require that they're orthogonal enough. So let's say the areas are off from each other sufficiently so that they're roughly orthogonal, so that you can patch together these Hilbert spaces and they don't overlap much. So there's some technical conditions on what that means precisely. But once you patch together these different states, then you can show in this larger code subspace that there's a version of approximate JLMS that's true. So in our paper, we considered general semi-classical states which would be contained in this larger code subspace, because we're just choosing to decompose them in this particular basis.
I'm trying to understand what happened here. You did
Yeah.
two things, right?
Yeah.
One is you were worried about exponentiating
Yeah.
the JLMS.
Yes,
and,
yes.
And that required that the projectors commute with a
Yes.
modular Hamiltonian.
Yes.
But the other thing seems to be like a re-derivation of JLMS. Can you remind me again what, in which way you go beyond the original derivations of JLMS?
Oh, for this one?
Is it the approximate error?
Yeah, it's the approximate because it adds in this new condition about the log stability. Like you need that, and then you can derive it keeping track of errors. And so this is the approximate QEC version of JLMS
Okay.
within the small code subspace. And then you patch them together.
Exponentiation
Yeah,
is what forces you to go to fixed area.
correct,
space,
correct,
And then you put it back together.
correct, correct. That's right. So it's like a technical trick to be able to do this exponentiated version. Okay, so once you have this, like you have sufficient orthogonality conditions, you can also show that there's approximate JLMS in the larger code subspace once you put these together, as long as you have a similar condition on this not too small eigenvalue, so you have log stable states. And similarly, you can prove this exponentiated version because you have fixed area states, but technically what you need is an imaginary Renyi version of FLM. So normally we talk about the entropy being given by the area plus the bulk entropy. It's the same, but now we need an imaginary Renyi parameter. This is something that's derivable from the path integral in a similar fashion as what Leuckwitz-Maldacena did, but now just for imaginary Renyi index instead of just real index. With that, you can derive this formula, which is the approximate exponentiated version of JLMS. So once we've thought about it this way, in this particular choice of code subspace, you have all the ingredients to understand modular flow in semi-classical states. So we have everything in place. So let's look at modular flow and see when it can be actually approximated by area flow. Naively, for a long time, I thought that always it's true that the modular Hamiltonian is just approximately the area, because we always say that the bulk correction is some order 1 thing and so on. But in this large code subspace, that's not actually true. And the reason it's not true is simple to see from this example. So let's say you consider BTZ black holes, and I forget about all other degrees of freedom except just the horizon area. You can just check that the modular Hamiltonian, which is just the Hamiltonian in this case, is quadratic in the area. And so when you decompose it into an area term and a bulk term, the bulk term has a 1 over g in it. And the reason you should think of it this way is that what's happening is when you have this large code subspace, you're keeping tails of this wave function, which are going to be pretty small away from the peak of the spectrum. And those fall off like e to the minus 1 over g. And then when you take a log, you have a 1 over g in there. So the bulk term in general can be competitive or even larger than the area term when you act on general states. However, when you're acting on states which are pretty localized near the peak of the spectrum, then because the probability is just an order 1 number, you can basically ignore this term.
I've got lost it.
Yeah.
Just considering two-sided black hole.
Yeah, yeah.
And you're saying the modular Hamiltonian is not given by the area.
The modular Hamiltonian is not given by the area.
What is this A beta?
Yeah, good. Okay, so maybe I should say that in more detail. So A hat is the area of the horizon. A beta is the area of the horizon at the peak of the spectrum. So it's like the expectation value of the area. So the thermal state will have some distribution which is peaked at this A beta, but it has some falling distribution. And what I'm saying is that near the peak of that distribution, you can approximate K to be A over 4G, but anywhere far from it, it's far from being so.
What's special about PKZ here?
It's not. I mean, this is just like a computable example where you explicitly see what happens. The important point was just that you'll have these long tails in the large code subspace, which you need to keep track of.
Yeah, so there's a bit of a shock now. So you're
Yeah.
telling me that in general, the modular Hamiltonian is not given by the
Yeah, I think the reason that we think intuitively that way is because we always think about taking the expectation value in the original state, which is sharply peaked at the same value of the spectrum, or even like if it's like small excitations or so, it's roughly peaked at the same location. And then you can basically drop this term.
Yeah, but so I'm just, if this, yeah.
Yeah.
But the operator version is used, I thought, in things like JLMS. Not just the expectation value.
Well, we all, whenever we, like every situation in the literature that I know of, it acts on the same state. Or like a close enough state.
Oh yeah, because you just vary the location.
Yeah.
Okay.
Um,
I'll try to recover.
yeah, I know. It took me a few days to digest this, but Dawn somehow was like, of course it's this way.
So the actual modular Hamiltonian is actually A squared?
Yeah, I mean, this is a trivial fact. It's just, it's just like, I mean, when you, like the area is like, I don't know, radius squared and like energy is like whatever. It's just like that translation. It's not like some deep fact.
Well, I don't know, you could have written the area cubed over A
Yeah.
squared. How did I know? Yeah.
Oh, that way. Yeah, I mean, that's just like an example. Like if you go to higher dimensions, you'll have like different powers and so on. So yeah, the BTZ is just like an illustrative example. The general point is just to say it's not A. Sorry to break your heart. Okay, good. But so the key point to remember is that, so that's the reason we have nice formulas only when acting on the same state. Like in general, you need to take into account the K bulk part when acting on other states, for example, and there's just no way you could expect that to be a simple formula. So this is part of why it has a nice geometric action. Do I want to say anything about this? Okay, so basically, so this part is just saying what I just said, which is we'll work near the peak of the spectrum. But I want to clarify a particular sense in which the modular flow is going to be approximated by the area flow. What I mean by that is that the classical background geometry agrees. So whether you do area flow or modular flow, the classical background geometries agree. But on the other hand, the quantum states are very different. So if you take into account correlation functions or things like that, those are pretty different. So for example, if you have two-sided correlation functions, the bulk modular flow will change them. But the area flow commutes with all of that, so the area flow doesn't change the correlation functions. On the other hand, like the vacuum at the horizon is destroyed by the area flow for reasons similar to what Raphael was saying before. And you need a regulator, a UV cutoff in the bulk to make sense of it. But on the other hand, the modular flow keeps it smooth. This is an argument by JLMS originally, which was basically that you boost on one side, but you also boost the fields appropriately so that it's not a singular state. So the only sense in which this is an approximation is that I'm only going to focus on the one-point functions, just the classical background geometry and the values of the classical fields. Okay. Okay, good. So now finally, I can tell you why the area flow gives you a Kink transform. And since we saw it's the same as the modular flow in certain cases, it's going to prove the Kink transform. Every discussion of the action of the area operator that I found before in the literature always considered situations where you have sort of a one-sided phase space where you add an explicit boundary at the horizon and just discuss like a wedge. But there's not any discussions which is relevant to holography, which is where you have this two-sided phase space and the area is like dividing it into two wedges. So, and the issue with that is it really obscures the importance of extremality. So we saw that in the Kink transform, extremality was really important to satisfy the constraint equations, and that really required gluing these two wedges together. And somehow this is something that people in classical phase space literature haven't ever cared about. So we had to sort of re-derive this, and a useful way to do it is to use the Peierls bracket. The Peierls bracket is a way to compute, I mean it's essentially equivalent to the Poisson bracket, but it's got a nice geometric picture, and it was sort of brought back into the limelight by a paper by Harlow and Wu. And the idea is what you do is if you want to compute the bracket between two operators f and g, you just add g to the action with some small coefficient. So here you should think of k as a small coefficient. So you're perturbing the action by adding in g and then looking at the response. So it's basically what you do in linear response theory. So you add g and look at how the fields change. So you can look at how, for example, f changes when you change this background. And you do this in two ways. You first hold the retarded boundary conditions fixed. So you keep the solution same in the past, look at the action of g in the future. That changes the value of f in some way. Then you look at the advanced solution where you keep it same in the future and then look at the effect on the past. So, and then you consider the difference. This difference is some linearized solution, and you can find what the change in f is when you combine these two effects. This is something that's analogous to like computing the Feynman propagator in QFT. Like you just look at the difference between the advanced and retarded solutions. And so it's the natural classical version of that Feynman propagator calculation. So this is how it's defined, and what we're interested in here is to compute the brackets of arbitrary operators with the area operator. And it so turns out that adding this area operator just creates a conical defect at the extremal surface. So a picture for the retarded solution is the following. You keep the solution the same in the past, then you hit this conical defect, which you can think of. So when you go from a Cauchy slice in the past, there's a kink that gets added onto the Cauchy slice in the future. So if you look at the effect on, say, the extrinsic curvature here, it's shifted by a delta function. And the advanced solution is quite similar. So when you consider the difference between these, just because of how a cone is, the induced metrics agree on these two regions, but the extrinsic curvature is shifted by precisely the amount that the Kink transform tells you. And so this is, so that tells you that the linearized effect on the initial data is to shift the extrinsic curvature by some linear amount, and then you can just integrate that flow and you find that it gives you the Kink transform. So what we've done here is looked at the flow using the Peierls bracket and derived that the area flow is actually giving you this kink because of the presence of these conical defects. There's a similar result that was derived in this paper using the Poisson bracket, but that doesn't have a nice, nice picture where you can see the effect of this conical defect. And moreover, the Poisson bracket doesn't generalize very well to higher derivative theories, and the Peierls bracket is a very useful technique to think about higher derivative theories because the same sort of calculations can be done there. When you talk about higher derivative theories, A over 4G gets generalized to what's called the geometric entropy, which was derived by Zhidong and then lots of follow-up work after that, which is the walled entropy plus some extrinsic curvature correction. So it's some functional of the theory that you care about, and it has higher corrections to just the area. Now, in general, it's complicated to define the action, the higher derivative action, for such conical spacetimes. And for Euclidean spacetimes, this was done in a paper by Xi and Dawn, where they provided a prescription to even define the action for conical spacetimes. And this was also used in Sean's paper where they derived the HRT formula. And well, long story short, you can basically try to do the same with the Lorentzian action and give a definition for the action for these conical defect spacetimes, but now in Lorentzian signature. Once you do that, then again, you find the same thing where the Peierls retarded solution is a cone. And because of the cone, we see that when you match the Cauchy slices across it, you get a Kink transform. There's one interesting feature that I'd like to mention, which is in some sense, this Lorentzian calculation of the geometric entropy seems to be quite different from the Euclidean calculation. For example, the Euclidean calculation is kind of messy. I hadn't appreciated this before working on this, which was that apart from just, when you consider a deformation of a shift in the conical defect angle, there's a linearized term that gives you the wall term, but there's like these higher second order terms that you need to be careful about, which give you these extrinsic curvature terms. It so turns out that the Lorentzian calculation is actually nicer in that you only look at the linearized piece and extract both the walled and extrinsic curvature terms. So it's sort of a more convenient derivation. And this we've checked in some dilaton gravity examples, but more generally, it's not completely clear yet. And then again, you need to integrate along the flow to prove the full Kink transform. This is just the linearized version. That requires some smearing in order to, again, make sense of the action and so on. And this is still an open end, which we're still working on, but I think it should be fine. So with that, let me summarize. What I've told you about today is deriving the Kink transform from the JLMS formula. And en route, we saw various subtleties. We saw subtleties with when JLMS holds an approximate quantum error correction, introduce these log stable nice states where it works. We built up a large code subspace for holography, which involved fixed area states. Showed that the modular Hamiltonian is only approximated by the area operator near the peak of the spectrum. And Lorentzian conical spacetimes were useful in deriving this Kink transform for arbitrary theories. So with that, I'd like to thank you.
Question. I have a question.
Yeah.
So this F11 formula, you had an imaginary random
Yeah,
index.
yeah.
Can you go back to that formula actually? So this area term is also some area of some cosmic brain with imaginary
Yes,
tension.
yes.
So both sides of this formula, everything's imaginary, like the quantities themselves are also
No.
imaginary?
The quantity, yeah, okay, good. So the area is a real quantity here. These two are imaginary.
I see. So should I give this formula some like information theoretic?
I'm not
Like, what does it
sure.
mean?
Yeah, I'm not exactly sure. Like, no one ever considers like imaginary index Rennies. Yeah, I don't have a good interpretation for them. Yeah.
That imaginary thing comes also from because you're looking at Rath and stuff?
Yeah, roughly. I mean, here we cared about it because you want, the imaginary piece comes because you want this e to the I kr, I mean, just to get something like that. But yeah, there is a difference between the Lorentzian signature action for a conical defect and the Euclidean one differs by this I. So
Sounds a bit like a replica in Euclidean versus what you do in Lorentz.
exactly, it's exactly that. Yeah.
I just have very comments.
Yeah.
So like in classical scattering, people study these like Regge approximations.
Like the iconal.
Sorry, it's not iconal. It's when you consider the scattering now, and you have some angular momentum, you continue angular momentum to be complex, and then study it in the complex plane, and then it tells you, something about the scattering, and it looks similar now that you're interested, like ultimately in the
here, maybe.